Okay, gentlemen, now in the previous videos we talked about operational properties of Laplace transform, right? How to shift about the s-axis and also how to shift about the t-axis and using step unit function to describe some piecewise defined functions as a single function. And after that, we use all the things to solve some different differential equations. Today, now we will start another type of operational properties. Okay, that is 7.4. So in this lecture, we're going to talk about derivatives of a transform and transforms of integrals and transforms of a periodic function. Okay, so as I told you, this direct delta function, it is optional. A systems of linear differential equation, there is not much to learn here. It will go very fast. It's almost finished. And next week, you will see, I try to finish this chapter, and also I'm going to introduce you with chapter 8 or 9. Okay. Okay, so now actually in this section we will develop some more operational properties of the Laplace transform, and specifically we shall see how to find the transform of a function f of t that is multiplied by a monomial t to the power n. Okay, t to the power n. Here we have f of t. All right, so now if our f function is multiplied by monomial, one term, that is t to the power n, how do we evaluate this? And of course, immediately you can just say that, okay, by using the definition, I can evaluate this. That's right. But some special functions, all right, when you just do this, there's a kind of pattern when you just change the power of this t. When t equals 1, evaluate this. When t equals 2, evaluate this. When t equals 3. So you will see the pattern. That means that now it is worth actually to generate a formula, and we don't have to use that long process or that formula or definition to get to evaluate this Laplace transform of the functions of this form. And that's why immediately we can use the formula. Actually, that gives us, that saves us a lot of time. So the first, let's start with this theorem. It says that if capital F of S is Laplace transform of f of t, and here n is positive integers, that is 1, 2, 3, 4, 5, 6, and here it's saying that then Laplace transform of t to the power n times f of t, we are given some kind of function here, is equal to just -1 to the power n, and differentiates Laplace transform of this function at f of s n times here. Okay, that is very, it's kind of shorthand and very good formula. And you will see that a lot of cases, if we have like 3, 4, when you use the definition, it is very, very long. Okay, so we're going to have a shortcut here. So now we are going to prove this. Why is this so? Assume that first, let's start with n. Here we have n is positive integer. And to prove this, let me use green. That is my one of the favorite color. Proof. Okay, let's do the proof step by step. And here we are going to see a pattern. And after that, we can generalize this and get this thing. So here, let's say n equals 1. Okay, now what we got here then? Here we have Laplace of t times f of t, right? And keep in mind that Laplace transform f of t is given here, capital F of s. So using the formula, what we got here? Here we have integral from 0 to positive infinity, e to the power st times what we have here, this function, right? Here I have t times f of t. And here we have dt. Okay, this looks like, let me just change it, t. Okay, just I need to evaluate this integral. How can I do that? To do this, here we have t. Okay. All right. Square of t. Okay. dfs. All right, good. Now I will stop here. Okay, I will use this a bit later. Okay, so now we'll do it in this way. Here we have f, here we have Laplace of f of t. What happens if I differentiate this capital F of s with respect to s? Okay, and that is equal to d over ds, right? And what is f of s is equal to Laplace of f of t. So here we have Laplace of f of t as equal to d ds. What is this thing? That is just integral from 0 to the positive infinity e to the power st times f of t dt. Okay. Now, if you remember from calculus, actually, this derivative and integral, we can interchange them. Okay, that means I can just bring this inside, or I can just take this out. So using the property of derivative and integral, I can just write it as integral from 0 to positive infinity. Here we have d ds e to the power minus st times f of t dt. Right? Now the thing is, here we have nothing to do with s, right? This is also nothing to do with s. Here we have s. That is a function of s. So if I differentiate this with respect to s, right? If I just differentiate this thing, right, with respect to s, what do we have here? So differentiate this, that is minus s. So here we have integral from 0 to positive infinity minus s times, right? Here we have e to the power minus st times f of t dt, which is equal to now minus s with respect to t is just a constant number. I can take this out. So here we have, okay, here we have equals minus s integral from 0 to positive infinity. Here we have e to the power minus st times, here we have f of t dt. And what is this thing? It is just exactly the Laplace transform of f of t, right? So now I can write it as minus s times, what do we have here? Laplace of f of t, right? So that is Laplace of f of t. Now from here, what we get here? So that thing is equal to, right? That thing is equal to Laplace transform, okay, f of s minus s, okay. Okay, good. We made one mistake here. Yes, because we got something wrong. Guys, get back to here. Here we are differentiating this thing, right? E to the power minus st with respect to s. So we are differentiating this thing with respect to s. S is a variable here. So here I need to have not s, I need to have here t. Right? So then what we got here? Minus integral from 0 to positive infinity e to the power minus st times, here I have t times f of t, t times f of t dt, right? And now in the definition of Laplace transform, we have e to the power minus st. Now instead of f of t, I have this function, right? And here we have minus, so that is equal to minus Laplace transform of, what is it? T f of t. right? So now from here, I can get that if you just multiply both sides, right? That means that if, let me just change the marker color. So Laplace transform of t times f of t is just equal to, take this minus to the left hand side, minus d ds f of s. Okay, that's the first thing. That means that if you are given f of t and its Laplace transform is capital F of s, if you want to evaluate this, you don't have to use the definition. Just if you know this, differentiate it and multiply by -1, you will get the result. Okay. Now, how about the second case is, let's say n equals 2. Okay. If n equals 2, what we have here, then here we have Laplace transform of t squared times f of t, right? We need to evaluate this. Now I will use the previous formula. That is equal to, I can write it as Laplace transform of t times t f of t, right? That is equal to, what is this thing? Now instead of f, I have this function. And it says that to evaluate this, just differentiate the Laplace transform of this thing and multiply by -1. So that is, here we have minus, right? And what is the Laplace transform of this thing? I should differentiate this, ds. Now here, Laplace transform of this thing. We have just calculated this as equal to minus d over ds. Here we have capital F of s, right? So now if you simplify this, what we got here? Equals minus minus is plus. So here they are differentiating this twice. So that here we have d squared over ds squared f of s. Okay. And how about when n equals 3? So here we have Laplace of t cubed times f of t, right? That's equal to Laplace of t times, I can write it as t squared f of t. So that thing is, that means that just differentiate Laplace transform of this and multiply by -1. That is minus, what is the Laplace transform of this? We have just evaluated this. So here we have d ds, right? And I need to write here d squared ds squared f of s. That thing will be equal to minus, that means that differentiate and differentiate twice. That means that we have to differentiate this thrice. So here we have d cubed over ds cubed, and here we have f of s, right? So when it is 1 minus, when it is 2 plus, when it is 3 minus, when it is 4 plus. So now we can generalize. There's a pattern here, as you see. So now, if you need to evaluate the Laplace transform of t to the power n is positive integer here, f of t, right? It is just equal to -1 to the power n times nth order derivative of f with respect to s, and here we have capital F of s, where Laplace transform of f of t is equal to capital F of s. Okay, that is the proof of this formula. Now immediately let's apply this to this question. Evaluate Laplace transform of this. So in this question, as you know, as you see, our f function is sine of kt, right? And what is f of s then? F of s equals Laplace transform of f of t, right? That is equal to k squared over s squared plus k squared, right? So now using that formula, that is a first observation. The second one is then Laplace transform of t times sine of kt is equal to, just differentiate this and multiply by -1, right? That is minus d ds, and that is f of s. Our f of s is k squared over s squared plus k squared. So we now have to evaluate this, right? That thing is minus k squared. Here we have to differentiate this. How can I differentiate this? Here we have s squared plus k squared to the power -1, and I have to differentiate this. It is this, right? Okay. Equals, first -1 comes to the front, that is k squared, right? And then we have to subtract 1, that is s squared plus k squared minus 2. Differentiate the inside, that is 2s, right? So what we have here then, that's equal to 2k squared s over s squared plus k squared, and here we have squared. All right. So now if you're given this, as you see here, finding it is inverse is not easy, right? So using this information, we can evaluate this. And how about if we need to find, for example, another question is, let's say you need to find this, Laplace transform of t squared times sine of kt, for example, right? So just that's equal to minus d ds, right? I have to differentiate this once. That is 2k squared s over s squared plus k squared and the squared, right? We don't have to use the integral because we know that integrating a function, differentiating a function, which one is easier? Differentiating a function is much easier than integrating a function. Let's make use of this immediately. Here we have cosine of 40. So remember this thing, we are going to use this formula. Yihing, are you there?
Yes, sir.
Did we differentiate this correctly? I think we didn't make any mistake, right? We have to differentiate this. K squared is constant. This comes to the front. It is plus. So it is 2s, so 2k squared. And I hope this is correct.
That's correct, sir.
Okay. Oh, I made one mistake here because in sine, here we have k, right? Not squared. Here we have k. Here we have k. So here we have k. Okay, 2ks. Okay, 2ks. Good. Now, guys, let's solve this question. Okay, I will finish the class with this. And I think also you may be tired. That much is enough. We will continue next week. So let's solve this question. How do you solve this? Again, let's use Laplace transform to solve this question. Now, if you get the Laplace transform on both sides, here we have Laplace of x double prime plus 16. Here we have Laplace of x, that's equal to Laplace of cosine of 4t, right? And we now have to evaluate this, that is s squared, capital X of s, right, minus s times what we have here. What we have here. It is this, right? Here we have s x of 0, right? Minus here we have x prime of 0. Plus, how about here? It is just 16 capital X of s. And Laplace transform of this cosine, we know that that's equal to s over s squared plus 16. Okay, this x of 0 is equal to 0, so that is gone. X prime of 0, that's equal to 1, right? So what we have here? Here we have, this is 1, so that is x of s, the common factor. These two things are common factor. So here we have s squared plus 1 times capital X of s. Now here we have negative 1, right? Take this to the right-hand side. I will have here 1 plus s over s squared plus 16, right? So now if we divide both sides by this, then our x of s will be 1 over s squared plus 1, plus here we have s over, why did I write 1 here? It is 16, right? It is 16, s squared plus 16, so it is 16. So here we have s squared plus 16, so here we have s squared plus 16 squared. Okay, so now we are familiar with the things, right? The first one is, it is just sine function, right? And how about the second thing? I can just write these two things as, here we have 1 over 4 times 4 over s squared plus 4 squared. And how about here? Here we have k squared. Also, I can write it as 1 over 4 times 4 times s over s squared plus 4 squared and the squared, right? The previous one is, as you see here, we have 2 times, if k equals 4, what do we have here? Here we have 8, right? 8 times s, so here we have k squared. It is 4 squared. So we need to have here not 4. So it is 2k should be. So if this one is 4, so this should be 8. So this should be 8. Okay. So now what is x of t? That is inverse Laplace of capital X of s, right? That's equal to, what is the inverse of this function? That is equal to 1 over 4. That is sine, right? It is sine of 4t plus 1 over 8. We have just evaluated this. When it is so, that's equal to t times sine of 4t, right? S squared. We have just evaluated this. T times sine of 4t, that's equal to, here we have 4, 8s over s squared plus 4 squared is 16 squared. So that is this thing. And of course, actually, to get used to this, you need to practice a few questions, then you can do it a bit faster. Okay. All right, guys, it is convolution. Also takes a lot of time. Let me stop here. All right, we will continue next week. Guys, I will let you know about our compensation classes. As I told you, we are going to have 4 hours of compensation class next week. And if possible, think and let me know which day is suitable for you. It is Monday or Tuesday or Wednesday or Thursday. It's up to you. Okay. Thank you very much. See you next week. Enjoy your weekends. Bye-bye.